Today I will cover balance on non-reactive processes. So today I will upload two videos. Another one is mechanical energy balance. So the mechanical energy balance is based on two books, the elementary chemical processes and the basics principle in chemical engineering. So within that slide, it's based on American unit. But this one is based on elementary chemical processes. This is based on SI unit. So this chapter present procedure for evaluating enthalpy, then internal energy, table of specific enthalpy, specific internal energy is not are not available for all the process species. So once this calculation have been performed, the energy balance may be written and solved as before. So we outline the procedure for solving energy balance problem that will be applied to both non-reactive processes and reactive processes. But reactive processes and the transient processes, balance on transient processes, will be covered by Dr. Farhan. So reference state, this is important. So recall that we can never know the absolute value of specific internal energy and specific enthalpy for a species at a given state. So specific enthalpy is the sum of the energy of motion of all, this is our Avogadro number, in 1 gram mole of the species plus the intramolecular kinetic and potential energy of all the atom and subatomic particle which identity cannot be determined since specific enthalpy equal to U plus PV, and we cannot know the value of U. We also cannot know the value of H at a specified state. Fortunately, we never need to know the absolute value of U or H at a specified state. We only need to know the delta U and delta H. So the sign for delta U, so the delta refer to a change of there's a limit or something to refer to, which is we call it a reference state. So when we do the energy balance, we need to choose the reference state as the something to base upon when we do the calculation. Because even if you look at the table in appendix B, we have steam table. Even the steam table is based on reference state. Steam table, what else we have? Table 10. Sorry, table B10. The one is for the integral heat of solution and mixing at 25 degrees. So the reference state is 25 degrees. Yeah. So how do you choose the reference state? That one will be covered later. But normally we choose reference state based on the inlet temperature. Wait. So continue. So talking about reference state. So why we need to choose reference state? Because we need something to uh, compare with when we do the calculation. So normally we choose reference state based on the temperature inlet.
I have a question. So maksudnya
Yes.
kalau cari reference step, dia memang any condition memang dia based on in the temperature ke so?
Yes. Normally we choose it based on temperature and form, either liquid, solid, vapor. Yeah.
Yes, sir.
Because later on we will learn about different state, meaning from vapor to liquid, liquid to gas. So the one require a reference state for each of the species ataupun each of the element. Later we learn about it. But what you need to know now is why you need to choose the reference state. And if you choose it, uh, it's any actually. Any value can be the reference state, but the easiest way, we choose the reference state because we want to to make the enthalpy or internal energy equal to 0 for the feed. Yeah, well, that's why we choose the specific temperature form for the feed. It's okay. So the values of U and H in the steam table were generated using this procedure. Even values in appendix B for the steam table is generated based on this uh, method lah, reference state. So the reference state for the liquid water is at the triple point. So the triple point, if you refer to phase diagram dia ada 3 penjuru. The triple point is at that in the middle between the 3 penjuru. At which point U was defined to be 0 according to table B7. So table B7 you need to refer to the book, appendix B, page, wait, B7. Yes, page 650. So according to table B7, water vapor at 400 degrees C. So 400 degrees C. Berapa bar? 10 bar. Okay, 10 bar. 400 degrees C is next batch. Sudah 651. 10 bar. Temperature di atas. So internal energy is 2958 kilojoule per kilogram. So suggest you just print out tu. Pendek B senang nak refer. Tak tebal pun. Please je. This does not mean
Dah
that...
ada, sir.
bagus. This does not mean that the absolute value of internal energy for water in the specified state is 2958. Because we cannot know the absolute value, meaning the actual value of this 10 bar 400 degrees C. Yeah. So the moment you get this value is actually best relative to water at the reference state. So the reference state for water for table B7, B5 ke B6 is H2O liquid 0.01 degree C 0.00611 bar. Kenanya ini tu is based on the triple point in the phase diagram. So from this reference state to H2O, this condition, delta U specific enthalpy is equal to 2958 kilojoule per kilogram. Ay, not masih. Okay. So relative to water at the same reference state, the specific enthalpy of water vapor at 400 degrees C and 10 bar is H equal to U plus PV. So since we have the value for U and plus P is the pressure resistor, V specific volume, unit conversion, then we have H or specific enthalpy equal to 3264 kilojoule per kilogram. So 3264 kilojoule per kilogram is the same as the value in the table B7, page 651. So the quantities of 8.314, okay, and 0.08314 are value of the gas constant expressed in different unit. This one is only available in hard copy books. Boleh tak cari dalam Google? Ada. You search for gas constant. Exercise 1. So suppose water vapor at 300 degrees C and 5 bar is chosen as a reference state at which specific enthalpy is defined to be zero relative to this state. What is the specific enthalpy of liquid water at 75 degrees C and 1 bar? Then what is the specific internal energy of liquid water at 75 and 1 bar? All right. So what we need to do, refer to table B7, the easiest. Search for 5 bar 300 degrees C. So 5 bar 300 degrees C is the reference state. So at 300 degrees C, 5 bar is okay. So since this is the reference state, so the H specific enthalpy is 0. So relative to this state, what is the specific enthalpy of liquid water at 5 bar and 1 degrees C and 1 bar? 1 bar 75. Berapa yang nampak? 314. Tengok dalam page berapa tu. 650 650. So at 1 bar 75 degrees C, specific enthalpy is 314.
300 C per bar.
114. Okay.
Punya pun enthalpy kan sa H ni.
Ya, enthalpy ni.
33065.
31.
Eh?
314.
314.
Ya,
Table
B7.
B.7.
Ya, B.7 yes. 1 bar 75
Oh,
degrees
1
C.
bar.
The H
Degrees
is
C.
314.
Yeah, 314.0.
Cik jawapan tu. Bila jawapan tu? Ni ya. 654. Tu bukan soalan apa. 100. Hmm.
Wow. That is fine. Okay. So H is 2751.
Two seven five.
Yeah, 2755.
Untuk 75C N1 bar sah.
Yeah, relative to 300 degree C.
Oh,
Yeah, relative to it. 300 degree C. So 300 degree C 5 bar is ni tadi. 5 bar 300. Oh, kaspat 650.
306.
5 bar 300. Alah. 3065. 3065 tolak dengan 314. Betul tak? Kita calculator.
Betul. Satu. 2751.
314 tolak dengan 3065. Ya, buat 751. So how about the internal energy? So internal energy, you can also use apa ya? V. Sorry. H equal to U plus PV. Boleh juga. Yeah. Or you can just use the table. If you choose to use the table, then you have the value here. 313.9 minus apa ya? Buat 803. So 2489, 2489 lah. 2489.1 actually. 2489.1. So observe that H and U are state properties of a species. That is, their value depend only on the state of the species, primarily on its temperature and state of aggregation, solid, liquid, or gas, and to a lesser extent on its pressure, and for mixture of some species on its mole fraction in the mixture. The state property does not depend. The state property does not depend on how the species reach its state. Consequently, when a species passes from one state to another, both delta U, delta H for the process are independent of the path taken from the first state to the second one. So now the hypothetical process path. This is just to introduce actually. We will go learn further about the hypothetical path. Sebab dia ada changes in temperature, changes in pressure, constant temperature, phase changes. This is all under non-reactive. Maksudnya dia tak ada reaction. Mixing of two liquid So all of this 1, 2, 3 berapakah mixing dia untuk ya dah mixing. Heat of solution and mixing, that one is later lah. Cuma number 5 ya, is reactive process. That one is different. So section 8 or chapter 8 in this book is for the non-reactive processes. So you will learn 1 sampai 4. So this is what we call the process type. So for example, compressing hydrogen gas from 1 atm to 300 atm at 25 degrees C is a type 1 process. Changes in pressure at constant T. Then melting ice at 0 degrees C and then heating the liquid to 30 degrees C all at 1 atm is a type 3 because it's phase changes from solid ice to liquid. Followed by type 2, which is the mixing sulfuric acid and water at constant temperature of 2 degrees C and the constant pressure of 1 atm is type 4. Salah tu. Ya, constant temperature. Patutnya changes in temperature, constant pressure. Type 2 process, you see. So once we know how to calculate delta U, delta H for these 5 type of processes. So how many processes? 5 processes. Process 1 until 4 is for the non-reactive. Process 5 is for the reactive process. You can calculate this quantity for any process by taking advantage of the fact that H and U are step properties. The procedure is to construct a hypothetical process path from the initial state to the final state, consisting of a series of steps of the given 5 types. Having done this, we calculate delta H for each of the steps and then add the delta H for the step to calculate delta H for the total process. Since H, specific enthalpy is a state property, delta H is for the hypothetical process path which we constructed for convenience is the same as delta H for the partially followed by the process. Later, dia ada diagram. The same procedure can be followed to calculate delta U for any process, meaning that this one. So this true path, this is the hypothetical path. If you can find this true path, let's say you have the data already for phenol. This is phenol, pH. Yes, phenol. You have the table for phenol changing from solid to vapor. Yeah. Then the hypothetical path here will have the same value as the true path. But since we don't have this data, we don't have data for pH. Normally we have data for water. That's why we call it state table. It's the most complete. Yeah. But for specific chemical like phenol, there are no table. So since there are no table available, then we need to do the hypothetical path to calculate pH. Phenol solid 25 degrees C 1 atm to phenol vapor 300 degrees C 3 atm. Okay, this is the explanation now. So what we do, what you need to do is from this condition, we reduce it. Oh, sorry, we increase it to the temperature to 42.5. 42.5 referred to melting point. Yep. Cari dulu. Where you get the information from table B1. Appendix B, table B1. Look for phenol. Phenol tu. Macam nak phenol? Ada ni. So phenol melting temperature is 42.5. So before we can melt the phenol, so we need to increase the temperature first. That's why the delta H1, the first process or the first step or the first process pathway is increasing the temperature to a melting point temperature. Once it's reached the melting point temperature, meaning you need to calculate the delta H1, then you need to change the form lah. So the change the form is process type 3, yeah? From solid to liquid at similar temperature and region. Next is we need to change it to vapor form, right? So to change the vapor form, you need to increase the temperature to the boiling point of the phenol. So phenol in liquid form similar, but the temperature is increased up to 181, the boiling temperature for phenol at the same pressure. Next is you change the phase change, process type 3 from liquid to vapor, but the target is 300 degrees C. So 300 degrees C, you need to increase the temperature. Now that the phenol is in vapor form, 181 or at boiling point temperature, 180 M, so increase the temperature to 300 degrees C. But 300 degrees C for phenol, the data is not available. The data in this book lah, elementary chemical processes. We don't have that data. The data is available in sekejap cari dulu. Untuk ada. Oh, tak ada. Confirm tak ada. So you need to find it in Perry Chemical Handbook lah. Perry Chemical Handbook Volume 2. Volume 2 is for the data, the table for specific chemical. Very thick book. Overall, I got seven volume. So next is once you determine the delta H5, so phenol now at is a vapor at 300 degrees C, 180 M. So since this is not yet target, the target is 380 M, so you need to provide another pathway here, which is phenol vapor 10 degrees C at 380 M. Yeah. So next, in order to get this through path or delta H here, so delta H, the true path is equal to H1 H plus H2 until H6 like this. So that is what we call as a hypothetical pathway lah. Oh, exercise 2. So for exercise 2, you need to draw, just illustrate lah. Just draw the hypothetical pathway. So let's say for nitrogen, let's say for nitrogen, 20 degrees C, 200 mmHg is heated and compressed to 140 degrees C and 40 atm. One of an infinite number of possible solution is heat, because there's a many solutions for this. So one of the possible solution is to heat the 200 mmHg from 20 to 140, then compress isothermally from 200 mmHg to 40 atm. So what you need to do is you need to draw the hypothetical pathway like this. Ay, nak ni mana? Yeah, like this. Start with the apa tadi? Nitrogen 20 degrees C, 200 mmHg. Then delta H, another one. So you need to write the true path first. So this is the initial, this is the target, so this is the true path. So underneath the true path, then you do the hypothetical pathway. So for this case, how many hypothetical pathway? It's only two, meaning hitting the nitrogen from 20 to 140. That one is delta H1. Then delta H2 is to compress the nitrogen from 20 mmHg to 40 atm. The same thing for number 2. The cyclohexane vapor at 180 degrees C and 5 atm is cooled and condensed to liquid cyclohexane at 25 degrees C and 5 atm. The enthalpy change for the condensation of cyclohexane at 80 degrees C, and one name is known. So for this number 2 here, exercise 2. So first thing you need to do is to cool the cyclohexane vapor. You cannot simply change the phase from vapor to liquid, but you need to reduce the temperature to 80.7 degrees C. So in this case, 80.7 degrees C for what nama temperature yang you see is critical temperature. Okay, so you need to cool the vapor to 80.7 degrees C. So reducing the temperature from 180 to 80.7. So at 80.7, the form, the phase is still vapor, but that one is delta H1. So for the delta H2 is to change the phase from vapor to liquid. So from vapor to liquid, that one happened at 80.7 degrees C. Still not the targeted liquid hexane, liquid cyclohexane. So at 80.7 degrees C, the phase change is referred to delta H2 now. So from the latest phase change, cyclohexane liquid 80.7 degrees C 180 M. Oh ya, 580 M ke 180 M? Oh, 180 M rupanya. Okay, then ada satu step lah. Ada pensel situ. Okay. So the first step is this one. We reduce the temperature first to 80.7. Yes. Next is at this temperature, the pressure is still 580 M. Since the enthalpy change per condensation is at 180 M, so we need to reduce this to 180 M. So this one is delta H2. Delta H1 at 180 M cyclohexane vapor, still vapor. Temperature is 80.7. Then we do the phase change. From this is a vapor to liquid. So at liquid, it's actually 80.7 temperature and 180 M. Yes. So from here, we reduce the temperature. This is another delta H to 25 degrees C. But the pressure is 180 M. Then reduce again. Sorry. Then increase the pressure. Because the target is 25 degrees C, 580 M. So here 25 degrees C and 580 M. So how many delta H? 1, 2, 3, 4 dan 5 lah. Yeah. So you have 5 delta H to calculate which is equal to delta H for the through path lah. Okay, you do for question 3 and 4. Procedure of energy balance calculation. Hmm, check. Sekejap eh. For procedure of energy balance calculation, most of the problem at the end of this chapter and reactive energy balance look very much like the problem in previous chapter. Energy balance for closed, open and mechanical energy balance given value of some process variable fit in conduct steam temperature, pressure, phase, amount of flow rate, component mole fraction, calculate value of other process variable. So starting in non-reactive energy balance, you will also be asked to calculate the heat transfer to or from the process system, which will require writing and solving energy balance. Okay. So procedure to do the energy balance calculation. Perform all required material balance calculations. So for material balance calculation, yes, this book have some, but not much. You need to refer to in this book the chapter or refer to previous slide how to perform the material balance. Write the appropriate form of the energy balance, closed or open system, and delete any of the terms that are either zero or negligible for the given process system. For a stationary closed system, drop delta EK and delta EP and neglect W or work if the system volume is constant. There are no moving parts such as impeller in the stir tank. Energy is transferred to or from the system by electricity or radiation. The one is for the closed system. For an open steady state system, drop delta EP if there is no. That's why delta EP, delta EK is referred to potential energy and kinetic energy. So drop delta EP if there is no appreciable vertical separation between the inlet and the outlet port, and drop shaft work if there are no moving parts such as pump, turbine, impeller, and no energy is transferred by electricity or radiation. In addition, if temperature changes of more than few degrees, phase changes or configuration occur in the process, delta EKG is negligible compared to delta U and delta H, so may be deleted from the equation. So meaning the equation, either it's a closed system or open system, there's an equation associated with this. So the first thing need to do is uh, to cross out or determine the delta EK, delta EP, WS. Is it zero or not? Yeah. Meaning to simplify the term. Number 3 is to choose a reference state, phase, temperature, and pressure. for each species involved in the process, if delta H or U for a species, if we look up in a table such as steam table for water, choose a reference state used to generate the table, otherwise choose one of the inlet or outlet state as the reference state for the species. That one if the question give you a process, an open system process. For a closed constant volume system, construct a table with column for initial and final amount of species and specific enthalpy energy relative to chosen reference state. For an open system, construct a table with column for inlet and outlet stream. Although the procedure is, what can I say, long, but later you will be repeating the same method, the same procedure. For any type of question, this is the procedure. Yeah, table, choose the reference state, calculate the U or H that you have inserted in the table. Then calculate U, so delta U and delta H. So delta U refer to final, this is small or mass. Then for open system is the enthalpy. Calculate any work, kinetic energy, induction energy term that you have not dropped from the energy balance. Okay. So kinetic energy, work, potential energy. That term you need to refer to the previous chapter. Yeah. It's under mechanical energy balance. Then solve for the energy balance for whichever variable is unknown. Okay. So example, acetone denoted as AC. Oh, cap. Untuk. Pak Datuk. Aduh. Is partially condensed out of a gas stream containing 66.9 mole% acetone vapor and the balance nitrogen. Process specification and material balance calculation lead to the flowchart shown below. So, okay, like this. So 100 mole per second, acetone goes into the condenser. So the acetone is in vapor form. So 0.669 mole over this 100 mole per second, 0.669 mole is acetone in vapor form per mole total. Then 0.331 of 100 mole is nitrogen. This is over total mole, this one. Then 65 degrees C, 1 atm. So it's divided into two, since this is the condenser. So the bottom outlet is the liquid. That one is important. Liquid come at the bottom, vapor come at the top. It's common sense. So from the 100 mole per second, it's divided into two, 63.55 mole acetone in liquid form per second, then 36.45 mole per second is the uh, outlet for the vapor. But for the vapor here, it's not pure. Some traces of acetone vapor is released to top. Yeah. So the question is calculate the keyword cooling rate. So this, since there are no material balance required, so we can skip step one. Next is the energy, simplifying the energy balance. So for this open steady state system, this is the equation. There are no moving part. So Ws is 0. Delta EP is 0 as well. The kinetic energy is 0. So the energy balance equation reduced to or simplified to Q equal to delta H equal to NIHI outlet minus NIHI inlet. Next is to choose the reference state. Okay. Next is choose the reference state for acetone and nitrogen. So in this case, the author choose inlet stream, nitrogen 65 degrees C 1 atm. So let's say you have two components, nitrogen and something else. Then uh, you need to have two reference state. One is for acetone, another one is for the nitrogen. So we write the reference state on top of the table. So it's acetone liquid and nitrogen in gas. This is from the question given. The okay. So you notice a zero here. Right? It's zero because of pilih apa dah? The zero because of the apa pilihnya? Okay, so in this case, the reference state for nitrogen is the inlet. Since it's inlet, then we can say that delta H for the H inlet for nitrogen is 0. Yeah. How about the acetone? For this example, the author choose the outlet stream for uh, for the calculation. That's why you see here acetone liquid is 0. So not the following table, the following point apart from the table. Nitrogen has only one inlet state. Okay. And okay. Uh, so for the inlet is only for acetone in vapor form. So Since the substance have acetone vapor, acetone liquid, then nitrogen. So there are no acetone liquid in the feed. That's why they put dash here. The n value are obtained from the flow chart. The flow rate of acetone vapor at the inlet, for example, is you just multiply 100 millisecond multiply with 0.669 mole acetone vapor per mole. Then you get 66.9 mole acetone vapor per second, which is this value. Since the nitrogen entering the system and liquid acetone leaving the system area at their reference state, we set their specific enthalpy equal to 0. 3 unknown specific enthalpy have been labeled and must be determined in step 5. So for the step 5, you need to determine each of the H, H1, H2, H3. So how to calculate? Yeah, how to calculate? Since there are no table available like the steam table for acetone, so we can use the MCP delta T. H equal to MCP delta P. Enthalpy equal to mass multiply with heat capacity multiply with the delta T. Okay. To calculate the three unknown specific enthalpy in the table, we construct hypothetical process path from the reference state to the state of the species in the process and evaluate delta H for each path. This is the part of the question you have not yet learned to do. We will show you the question of the H1 to illustrate the method, give the result of the other calculation, and go into detail about the required procedure in section 8.2 to 8.5. So this is the first one, H1. So H1 is the specific enthalpy of AC. This is one. Okay. What else? Okay. So for H1 refer to this in the for AC vapor. Oh, so okay. This one. So delta H equal to MCP delta T for a change from delta H equal to CP delta T. So for a change from T1 to T2 at constant pressure, familiar for CPT, the heat capacity at constant pressure are given in table B2. Familiar for acetone liquid dan acetone. So acetone macam nombor 1 dalam table B2. Acetone. This is referred to table B2. Oh, number 1. Compound number 1. Last sekali. Page 635. So AC have two form or two state. It's either liquid or gas. So for liquid, you need to use Office Form 2 or Equation 2, but the value for ABCD ni. So for CP of acetone liquid, the value is until B. If you see page 635, there are two forms of CP, A plus BT plus CT square plus DT square DT cube, or A plus BT plus CT square. So what you need to do is plug in the value into the equation form 1 or form 2. Yes, it's form 1. Yes, form 1. Oh, sure. Step 5. So that is for the H1. Next is the H2. To calculate the three unknown specific enthalpy in the table, we construct a theoretical path from the reference state to the state of the switch. So in this table, this is the reference state. So this is the state, the targeted state lah for H2, H3. So table B1, okay. Delta HDB as delta H for liquid to vapor at normal boiling point TB. Table B1 lists TB. TB refer to boiling point. For acetone is 56. Delta HB heat of vaporization is 30.2 kilojoule per mole. So all of the data is available in table B1. Look for look for sini dah. TB for acetone, then delta H B heat of vaporization at boiling point is 30.2. Normal boiling point in C and heat of vaporization is at the normal boiling point is kilojoule per absorptive. Okay. No need, you can refer to table B1. So this is the process path from the reference state SCL 20 degree C 5 atm to AC vapor 65 degree C 1 atm. So ACV 65 degree C 1 atm is referred to this one H2. H2 ke H1? H1, sorry. H1. So how many H? Oh, sorry, enthalpy need to calculate 4. You get the delta, the true path lah, we say true. So next is substitute the value of VAC and delta HB, and we'll look for CPT integration of for H1. The ordinary equation we obtain H1 equal to 35.7 kilojoule per mole. So to calculate H1, sorry, H2 and H3, H2 and H3, it's the same. We have to get the value. If it's not given in table B1, then you need to search it in table B2 using the MCP delta T. For acetone, it's easy. It's the first compound. The table B2. Next, once you have all the H, the specific enthalpy, you need to calculate the rate, delta H here. Equal to N is referred to this one, either N in or N out. So this is an N out. And you get negative 23 to 2320 kilojoule per second. Calculate the non-zero work, kinetic energy, potential energy, which is non-resistant, then solve for Q. So Q equal to delta H equal to negative 2320 kilowatts. So before we leave this section, let us consider what we just did from a different perspective. The process for which we need to calculate delta H equal to Q may be depicted as shown below, like that. Yeah, from here to here. The H in effect, we can construct the following process path. This is the process path that we do to calculate this. The total level change for the first step, delta HA is the negative of delta H. For the process in which acetone and ethane go from confined condition to the inlet condition. Similar, delta HB is the enthalpy change for the process in which acetone and hydrogen go from the reference condition to the optimal condition. As enthalpy is a state function, the overall enthalpy change for the process must be this. Okay. So, you have any question, you can ask. Let me share the kan stop ini ya itu. Okay. Hmm, good morning, sir. For the last 4 weeks, we joined class at 9 a.m. until more. But in the part didn't see any meeting, so we thought there was no class. Ah, I think the last few week is video. Yeah, video. Only the first meeting I do online. So next week is the same. Yeah, one hour, 1 hour and a half. Mm, just need to know how to conduct the test actually. Yeah. If we cannot do it in week 6, maybe week 7. Mm. Class start at 10. Is it at 9 in the elite? 9. Oh, better change. Oh ya, 9. 1912. Alamaknya. Okay, I think that's all. Later I will upload 2 video. First one is mechanical energy balance. Another one is this recording. So thank you. If you have any question, you can meet me in my room. Wing A, room 30.